The long and sinuous Mount Hamilton Road acts as the gateway to the Lick Observatory. Those who dare to accept its challenge are awed by the sight of the observatory's impressive domes. Domes that house some of the most powerful astronomical research tools of the 20th century. For over 100 years, Lick Observatory has been at the forefront of astronomical discovery.
The Lick Observatory is the premier optical infrared observatory of the University of California, located in California. It serves all the campuses of the University of California with astronomers, with observers, and serves to do forefront research in astronomy and astrophysics with the variety of telescopes we have up there.
Astronomical research is the primary mission. In pursuit of this mission, Lick Observatory has proven itself a leader in development and fabrication of some of the world's most advanced instruments. Many generations of astronomers have come here to learn their trade. Many of the observatory's facilities are located at UC Santa Cruz, which accommodates over 150 faculty, staff, and graduate students. It includes extensive shops and laboratories for supporting astronomical research. Remaining on Mount Hamilton are maintenance and support personnel, their families, and of course, the telescopes. But to explain how such a remarkable observatory came to Northern California, the extraordinary life story of James Lick bears telling. From Pennsylvania woodworker to eccentric California millionaire. James Lick was born in 1796 in Fredericksburg, Pennsylvania. His father was a cabinet maker who taught James a trade that would serve him well. He spent his early years in South America, where he built beautiful pianos for nearly 30 years. Eventually, he returned to the United States to a small seaport town called San Francisco, bringing with him his workbench and his life savings of 30,000 Peruvian gold doubloons.
Well, when he arrived in January of 1848, San Francisco had just recently been called Yerba Buena. It was a tent city, and it had fewer than 1,000 people. 17 days after he arrived, gold was discovered at Sutter's Mill. And after a while, James Lick, like everyone else, went off to the American River, inappropriately dressed in his stovepipe hat and greatcoat that he always wore, and he lasted 3 days. And he decided that his gold lay in San Francisco.
James had arrived by ship, but his doubloons weren't all that he brought with him. He had 600 pounds of chocolate on consignment from his neighbor in Peru. The chocolate sold quickly. On Lick's advice, San Francisco became the new home of the esteemed confectioner Domingo Ghirardelli, a name that has become synonymous with San Francisco.
It didn't take very long, probably within 2 years before James Lick was a millionaire. And by 1857, San Francisco was a big, booming town with regular buildings and wooden sidewalks and businesses.
Furthering his fortune, he built an enormous flour mill in the Santa Clara Valley that supplied Californians with the finest flour. James settled in Santa Clara because he liked its climate and the Guadalupe River.
James Lick had built a replica of the conservatory at Kew Gardens, which he had seen and admired. And of course it went along with his interest in horticulture, his interest in flowering bushes of all kinds. He intended to give this as a gift to the city of San Jose, but he was enraged when the newspaper printed an article that ridiculed him, so it remained packed in boxes until businessmen from San Francisco, after his death, bought it and had it erected in Golden Gate Park as the Conservatory of Flowers. In 1873, James Lick had a massive stroke, but even before then he had been pondering what to do with his fortune. $3.5 million, a gigantic amount of money in those days. He liked monuments, and he took it into his head to build on the corner of 4th and Market a pyramid larger than the Great Pyramid of Egypt to honor himself and his parents. You can imagine what the scientific community thought when they heard of that. And we do know of 3 men of science who influenced him to leave his money to science, and especially for a telescope. So he looked at the heavens through this young man's telescope, and he was enthralled with what he saw. And the young man said to him, "Mr. Lick, if I had your money, I would build the greatest telescope in the world."
And so, James put in place a board of trustees to build the Lick Observatory. Sadly, James died in 1876, 4 years before construction could begin on what would become his most impressive monument. In the 1800s, most observatories were located near universities, which were low in elevation and subject to atmospheric disturbances. Lick's Board of Trustees realized that Mount Hamilton's clear skies and high elevation were superbly suited for the world's largest telescope, and so Lick Observatory was to become the very first permanently occupied mountaintop observatory. The actual work of building the observatory began in 1880. Using bricks fired in mountaintop kilns, the main building began to take form with the raising of the dome for a 12-inch telescope. The long central hallway of the building advanced southward along the summit as construction progressed. But then, at the point where the hallway was to meet the 36-inch dome, construction halted abruptly. The glass for the two elements that would make the giant lens had been quickly produced in France, but one was accidentally broken during shipment. Without the glass, the length of the telescope could not be determined, and the required dome size remained unknown. It took nearly 18 attempts and several years to replace the lens. But late in 1886, the largest lenses ever made arrived safely on Mount Hamilton. Construction resumed immediately, and the great 36-inch refractor was finally unveiled in 1888. The telescope's tube and mount were contracted to Warner and Swasey of Cleveland, Ohio. It took 3 weeks of precision work to hoist the pieces into place. When assembled, the telescope stood 57 feet long, 4 feet in diameter, and weighed 25,000 pounds. A telescope of this size presented a unique problem. When the telescope pivots on its axis, the eyepiece might swing very far above the floor level, higher than would be safe to reach from a tall ladder. The solution was to elevate the massive 3,500 square foot floor to follow the motion of the telescope. In 1888, this was ingeniously accomplished by water power.
This telescope was one of the premier research telescopes of the University of California for nearly a century. And during that time, it was involved in a very wide range of projects. The telescope was particularly involved in measuring the motions of stars within the Milky Way galaxy, particularly those closest to the Earth. And also is very heavily involved in categorizing the types of stars that are members of the population of the Milky Way. The most spectacular discovery of all for this telescope came very early in its useful life. It went into operation in 1888, and in 1892, after nearly 300 years of everybody believing that Jupiter had 4 moons, the 4 bright moons discovered by Galileo in 1610. It was to everybody's great astonishment a 5th moon was discovered here with this telescope in 1892. The discovery was made by a man with very keen eyesight, just looking through the eyepiece under the best possible atmospheric conditions. And that discovery made Lick Observatory world famous. It brought Lick Observatory to the awareness of people throughout the world.
Many people still consider the 36-inch refractor to be synonymous with Lick Observatory, and for good reason. It was the world's premier telescope when first built, and remains to this day the second largest refractor in the world. It has also come to stand for the achievements of late 19th century astronomy. The telescope's powerful mystique is heightened by its role as the tomb of James Lick, who lies buried at the base of the Great Refractor. Telescopes owe their longevity to the fundamental simplicity of their job, gathering and focusing light. It is the ever-evolving instruments attached to them that prolong their life as research tools. For example, the observatory's 120-year-old Crosley reflector, equipped with modern instruments, continues to provide useful scientific data. Though not the first telescope on Mount Hamilton, the Crosley reflector is the oldest and arguably the most influential. It is distinguished by several pivotal contributions to late 19th and early 20th century astronomy. The Crosley was originally built in England by amateur A.A. Common in 1879, and with it he made a magnificent observation. Through photography of the Orion Nebula, he found that stars too faint to be seen with the naked eye could be seen in the resulting photograph, using the same telescope under the same conditions. Common sold the telescope to Edward Crosley, who in turn donated it to Lick Observatory in 1895. In an effort to maximize the Crosley's potential, Lick's astronomers rebuilt the original weak and flimsy mounting, encasing it in a solid tube mounted to a sturdy pier. Another of the Crosley telescope's major contributions came from James Keeler, who used it to photograph bright nebulae. Keeler's photographs revealed many faint nebulae in the backgrounds. He showed that whatever their nature, nebulae are a major constituent of the universe and not just an occasional oddity. This was pivotal in opening up the field of extragalactic astronomy, an area which has been of the greatest interest to astronomers ever since. Keeler's exquisite photographs also played a major role convincing the astronomical community that large reflectors were the best choice for most research purposes. Mirror technology is still the preferred choice for modern research telescopes. All stars move, and careful study of their motions tells us a great deal about our galaxy. The 20-inch Carnegie astrograph was built expressly to measure the motions of as many stars as possible in the surrounding part of our own galaxy, the Milky Way. The Carnegie is actually two 20-inch telescopes side by side on a single mount, both pointing at the same part of the sky. The two telescopes are refractors with lenses optimized for focusing blue and yellow light respectively. Two photographic glass plates are exposed simultaneously to capture complementary images. The telescope's original project was called the Lick Proper Motion Survey, which called for photographing the entire sky twice, once in the early 50s and once again 20 years later. The plates are compared to determine the motions of stars and thus derive new information about the structure of our galaxy. Although less used now, the telescope remains a valuable tool when photographs of a wide area of the sky are needed. By the 1930s, Lick's facilities were growing outdated and less able to compete with the larger, more modern telescopes at other institutions.
The 200-inch telescope was the major advance in telescope size that required the development of a new glass called Pyrex. And along the way to the development of the 200-inch mirror blank, they poured a 120-inch blank out of Pyrex and stored it away. Years later, University of California astronomers got interested in building a large telescope, remembered that blank existed, and that was the beginning.
The largest dome on Mount Hamilton is located a half-mile east of the main building. Within its walls stands the Shane 120-inch reflector, Lick Observatory's largest and most powerful telescope. It is often supposed the telescopes are used to make distant objects appear closer, but it is more accurate to say that they make faint objects appear brighter. The 120-inch reflector emphasizes light gathering over magnification. The challenge is to collect enough light to make measurements possible.
Well, the primary mirror is just the beginning. It's a big beginning because it's the single most expensive thing in the telescope usually. In the case of the 120-inch telescope, we had to build an optical shop that is a shop that could work on the glass itself and convert it from a raw blank, a raw disc of glass, into the polished surface that makes it work. And it had to be polished to an accuracy of about 1/millionth of an inch over this entire surface, 10 feet in diameter, in order to perform as it does. The next crucial thing, though, is to hold that mirror in a very rigid way. That requires a very heavy mounting, very finely tuned motor controls that compensate for the Earth's rotation, and the whole rest of the telescope it took as much time to build as that primary mirror took to grind. So the main collecting element, the main optical element of the 120-inch telescope is a mirror 120 inches in diameter that has a gentle curve in it. And that curve is just enough such that when light strikes it, it reflects off at a slightly different angle, and all around the mirror the reflections are such that they all come to a point at a focus at the top of the telescope. That's called the prime focus. In order to use bigger, heavier pieces of equipment, we've installed a second mirror at the top of the telescope, which reflects the light to a new focus behind the primary mirror. In other words, it goes up the tube to this mirror, reflects off, goes back down the tube to the bottom, through a hole in the primary mirror, and comes to a focus behind it. And there we've been able to locate a number of instruments that are quite large, heavy, and would never fit in the top of the telescope at the prime focus. We can also insert an auxiliary mirror, a third mirror, that intercepts the light after it's gone down the telescope to the primary mirror, up the telescope tube to the secondary mirror, halfway back down the tube to a third mirror, which reflects the light to an enormous spectrograph or instrument underground below the observatory. And that's called the Coude focus.
When quasars were discovered in the early 1960s, the 120-inch was the second biggest telescope in the world, a brand new young telescope having been completed just a few years earlier. So it was a natural telescope to study quasars with. And staff members were some of the very first people to identify optically these quasars and measure their redshift, establish that they were very distant. And for a long time, in fact, the most distant quasar known was measured at Lick Observatory. And Lick Observatory has been one of the major galaxy research centers. My surveys of elliptical galaxy structure were all done here with the 120-inch. On dozens and dozens of nights of observing time, using an instrument which was the first of its kind in the world. The Wampler-Robinson scanner was like a TV camera, took a TV image essentially of the spectrum, and all of the data came down over wires to the control room in the computer. It was the first remotely operated instrument in the world, and it was very sensitive, and without it I could never have made my observations. And in fact, the whole mode of observing there at Lick during the 70s has now been copied by every other observatory in the world.
The 120-inch reflector was the world's second largest telescope when completed in 1959. It catapulted Lick's observational capability back onto the scientific front line, where it remains today. At the north end of the main building, opposite the Great Refractor, stands a smaller dome that originally housed a 12-inch Clark refractor. Since 1979, it has been home to Mount Hamilton's second largest telescope, the 40-inch nickel reflector. This modern telescope was designed and constructed entirely in the Lick Observatory shops at UC Santa Cruz. It has relieved some of the demand for time on the 120-inch because it's suitable for projects that don't require the larger telescope's light-gathering power. It has also proven particularly useful in giving UC graduate students hands-on experience with modern equipment. The 40-inch is well equipped with up-to-date instruments, computers, and a control room adjacent to the dome. The newest telescope on Mount Hamilton is the 30-inch Kate. This unique robotic telescope is so fully automated that no human interaction is required for its routine operation. The Kate's night begins with an automatic check on the weather. If the weather sensors find it satisfactory, the dome opens, the telescope takes aim, and an exposure begins, all under the independent control of a computer. Through the night, the telescope observes a series of pre-programmed targets, making images of each, storing the data in the computer's memory, and even comparing them with reference data to look for significant changes. When something is found, scientists at UC Berkeley are notified automatically by email. In the morning, the Kate closes its dome and puts itself to bed. A new technology called adaptive optics is being developed at Lick Observatory in association with Lawrence Livermore Labs.
The purpose of this project is to get rid of distortions due to atmospheric turbulence, the effect that makes stars twinkle and dance around and makes them fuzzy blobs instead of sharp points.
The power of this technology lies in its ability to correct atmospheric disturbances in real time, allowing astronomers to take pictures nearly as sharp as those taken from space. The system being developed at Lick uses a combination of specially designed high-speed computers, mechanical actuators, and laser technology.
So the idea is that before the atmosphere can change, you want to measure all those little crinkles in the wavefront and put an equal and opposite crinkle in a deformable mirror located in the telescope axis.
The deformable mirror is mounted at the bottom of the telescope. It uses over 100 mechanical actuators that push on the back side of the mirror 100 times per second.
So the project then is to take a high-power laser and make a very small spot at the upper atmosphere and have the telescope look at that spot and determine how fuzzy it is and what its wavefront looks like. If there is not a bright natural star in the sky near to a dim object that you want to look at, you have the option of putting the laser any place you like. So you have complete freedom to do that.
The laser itself is bolted to the side of the 120-inch reflector. Late at night, the laser beam can actually be seen bolting out of the dome into the dark sky. Adaptive optics is just one of many techniques used by astronomers to help make measurements of the universe. Most modern research instruments fall into two basic categories: cameras for taking pictures, and spectrographs which analyze the light from celestial objects.
Spectroscopy is probably the most useful single tool in the astronomer's toolkit. When you remember that astronomers have only light to work with coming from the stars, it is an extraordinary piece of good fortune that there is so much information in light. There's a phenomenal amount of information if you know how to look at it. With a spectrograph, one can take that mixture of colors and spread them out into the constituent colors so that in fact you can see each color individually. What we're looking at here is a diffraction grating. This is one of the most important components in astronomy and the heart of every spectrograph. And it is producing spectra. The rainbow that you see are in fact spectra. We are literally standing inside of a spectrograph here. This is the Hamilton spectrograph. This particular spectrograph is it's quite extraordinary. It's one of the best of its kind in the world. It has done a great many different kinds of projects, but probably the most interesting recently, and certainly the highest profile, has been the discovery of planets around other stars. Until a couple of years ago, the only example of a solar system we had in the universe was our own. We suspected that there were planets around other stars, but it's a very, very difficult job to detect them and requires an instrument like the Hamilton and many years of hard work and dedication to discover more planets around other stars here at Lick than have been discovered anywhere else in the world.
In addition to spectrographs, astronomers use CCD cameras to image celestial objects.
At Lick Observatory, we build these enormous $5 million instruments for the Keck telescope. And to make sure they work, we built smaller versions of them here, and that's part of what this is. This is a bit of a prototype camera. We can image objects which are about 10 million times fainter than what you can see with your naked eye when you go out at night. So we spend all of our time looking at things that if you just go up and look at the sky, you'd never see them at all. They're much fainter than you can see without a telescope and a sensitive camera.
Well, Lick Observatory is a place to test forefront technology, new technology, in a situation which is far less forbidding and complicated than the top of Mauna Kea, which is 14,000 feet and a difficult place to work. So in fact, this adaptive optics system was a prototype for the adaptive optics system we're now building for the Keck telescope. The question came up as what is the best way to use Mount Hamilton in the future? Well, as it turns out, the infrared, the wavelengths of light beyond the red, are very important astronomically because they can reveal to us a lot of information about astronomical objects that optical light doesn't show us, doesn't reveal to us. It also turns out the night sky at Mount Hamilton in the infrared is as dark as any place. We're at no disadvantage at Mount Hamilton in what is called the near infrared. And that means that we should fully exploit, and we plan to fully exploit, the infrared part of the spectrum, building a new infrared spectrograph for the 120-inch telescope.
Well into its second century, Lick Observatory continues to produce the kind of science that brings us closer to understanding the mystery of our universe. James Lick's dream has become a historical landmark, one which has earned a reputation as a world leader in astronomical research.